All right, thanks all for coming. I'm going to do a quick tutorial on diffusion models for image generation. So I'm not going to show you any nice images or any such thing. This is just about the mathematical foundations of diffusions. This is not about using these generative models for posterior sampling. That's a separate topic. There's actually very recently there's been some tutorials. Alex and Yanis and others have some tutorial which is pretty comprehensive in that space. I'm not going to try to cover any of this. So today I just want to talk about how SDEs or stochastic differential equations are used for generation of images. That's all the goal for today's presentations. Okay. So the motivation is that images can be, so basically images are just vectors, very, very high dimensional vectors. If you think of a 512 by 512 image in 3 colors, then this is roughly a vector in 800,000 dimensions. And if you want high resolution, well, scale this vector appropriately. Okay. And so there are many tasks you could have in this kind of a thing. For example, generate a new image X. So that's really what we are going to be focusing on today. Meaning, so what does that even mean in this context? Well, one way to interpret generate an image is, well, there's the space of 800,000 dimensions, but presumably not every 800,000 dimensional vector is an image. It's some very small subset of that is an image. I'll use the word manifold, which is what everybody uses. I'm not sure why it's a manifold, but we'll use the word manifold for images. And so you want to sample from all possible natural images, and you want the sample. So let's call that distribution P0. That's the distribution of natural images over vectors X, which are in 800,000 dimensions. So I want to sample an X from that. There could be other questions you could ask as well. I don't want a sample of X. I want a sample from P of X given some information, some Y, which is a measurement, or P given Z, some text. These are all either called posterior sampling or stylizing or something else. You can use a generative model to start solving these kinds of problems. And these are generally called posterior sampling. Today, I'm not going to talk about any of these posterior sampling problems. I'm just going to talk about straight up, how do you generate? Okay, so this is the problem. I want a sample from some distribution P0, where I will always use P0 for the distribution of images. And the approach is going to be the following. I want to sample from this distribution. I don't have access to this distribution. But what I'll try to do is to construct a Markov process. So I'll do everything in continuous time. All this can be discretized, and in practice, everything works in discrete time. But I'm going to do things in continuous time. Okay. I want to construct a Markov process, which I'll initialize in some random manner. And if this Markov process is stationary ergodic, presumably as time tends to infinity, it will converge in distribution to some distribution pi. I want that distribution to be P0, the distribution of images. Okay, so that's the goal. Construct a stochastic process and evolve the stochastic process. Look at the distribution of the stochastic process. As t tends to infinity, this distribution should be the distribution of images. Again, stop me at any time if you have any questions. If you are online, Litu will be monitoring questions. So Litu, you can sort of maybe translate questions which are coming. And the Markov process we are going to use here are stochastic differential equations. In particular, what we are going to do is to do 2 different things. First, we are going to construct a stochastic differential equation that converts, whose initial condition is a sample of an image from distribution P0. Then you evolve this Markov process or stochastic differential equation, and you want it such that as t tends to infinity, this Markov process, the distribution of this is that of just standard Gaussian noise, N01 or N0I if you are dealing with vectors. We are going to construct a second Markov process, which starts from the initial condition is Gaussian, and as time evolves, as t tends to infinity, this Markov process stationary distribution is going to be P0. We are going to do these 2 constructions. Okay. But before we do any of these things, we are going to talk about the basic calculations with a stochastic differential equation and how its density evolves. So the outline of what I want to cover today is, first, what is a stochastic differential equation? Second, I think the most important thing I'll cover today, which is the Fokker-Planck equation, which says that how does the PDF or the probability density function of an SDE evolve? So SDE is just a stochastic process. It's a random sample. And as time evolves, the sample is different. But at each time, you have not just a sample of a random variable, but also a density of that. Meaning, if you run many stochastic, Markov processes, across all of them, there's some distribution. So that's what I want to understand how the PDF or the density of that evolves. That's going to be the Fokker-Planck equation. Then we'll apply this to a very classic SDE, which is called the Orsi-Nulenbeck process or the OU process. It will be initialized with x0, the sample at time 0, as a sample from the distribution of images P sub 0. We'll talk about how to reverse this to generate images. The reverse will require access to a certain black box, which is called the score. We'll talk about how to compute the score, which is used as a drift of the stochastic process. Again, I'm going to define what drift is in a minute. Finally, these are all sort of stochastic ways of doing things. Can we do ODEs, ordinary differential equation, not SDAs, and come up with samplers? These things are called flow models, and I want to show you how to take an SDE model and convert it to a flow model and vice versa. So nothing I'm going to be talking about today is any original work of my part. This is completely a tutorial. The references are there in these notes, which will be available offline. And much of the applications to the images are over the last 10 years. But the theory itself is classical, much of it, and goes back to 1950s, at 60s and 70s. Okay. So in terms of just textbooks, if you want to read something on stochastic differential equations, I would suggest Oxendaal's book on SDEs. It's a very approachable book. There are many more, of course, advanced books, but this is a great book to actually get some good understanding. There are also very nice tutorials on the web for other treatments of what I talked about. One which I really like is by NSF on diffusion models. He's at UCLA and SNU, and slides are available online, and I found them very useful when I was writing these. Then several other papers, and of course, Litu helped me a lot in this discussion, folks. So getting to the content itself. First, let's start talking about an ordinary differential equation. So what you have is dxt is mu xt comma t and dt. What does this mean? We call this mu as the drift term. Because when you are in some point xt, this is saying that there's a vector field which could be time varying and spatially varying, and it tells you, mu tells you which way it points it, and in a small interval of time, if you are here, you would move here. That's all an ODE is saying. Okay? So we'll call this mu as the drift term of this ODE. Roughly, this means that in a very small time interval, t to t plus h, xt plus h minus xt is roughly mu of whatever that xt is times h plus other h square and other terms. Okay, that's roughly your intuition of what an ODE is. So what is an SDE, or a stochastic differential equation? It has such a drift term, but you're also adding a little bit of noise at each time, meaning you're drifting according to mu, but then you're adding a little bit of noise. So think of dBT as just a little bit Gaussian noise with very small variance. Zero means Gaussian noise with small variance. We'll be a little more precise in a second. Okay, but you're just adding a little bit of Gaussian noise, and sigma says that the amount of variance that you're adding could depend on time and space. And so you're not just going down according to SD, according to drift. You're also you're going off in a random direction a little. So I'm going to call this, as everybody else calls it, this is the drift term, and this is called the diffusion term. And this is an SDE, and I need an initial condition. The initial condition I'll call P sub 0. We'll interpret P sub 0 for a while as the distribution of images. And we can think, so these are xt is a vector. For images, we are talking about 800,000 dimensional vectors. Okay, so let's be a little bit more specific about what this dBT is. So BT is formally Brownian motion, and it has these following three properties. So it is equal to 0 at time 0. And if you look at a small interval of time t to t plus s, if you look at BT between time interval s to t, then this is a sample of a Gaussian, and it's zero mean, and the variance is proportional to the time interval. Okay, so its variance is t minus s. It also has something called the independent increment property, meaning if you look at the Brownian motion trajectory over disjoint interval of time, they're statistically independent. So that's all I'm going to use about Brownian motion for doing stuff. So what does this mean, though, when I sort of look at small intervals of time? So let's do an expansion, xt plus h minus xt. So I'm using capital letters always. If it's a random variable, I use small letters for deterministic quantities. So I'm looking at along a sample path, along a trajectory, xt through xt plus h is roughly the drift times the time interval. So t plus h minus t. The diffusion coefficient times the difference in the Brownian motion, bt plus h minus bt, plus many other higher order terms will depend on this thing square, product of these things, and all this stuff. So far, there's nothing new. I mean, this is like what exactly the discussion I had for ODEs. But there's something important to note in this, which is if you now look at this, the reason we ignore any of these kinds of things normally. Well, let's look at t plus h minus t whole square. Okay? So this is basically just h square, which is negligible with respect to h, if h is small. Suppose I had some function which was smooth. Okay? And then I was looking at the difference in that function over a small interval of time. Constantine?
So just in terms of dimensionality, B says scalar, dimensionality of the vector.
What is a scalar?
BT plus
no, it's a vector. They're all vector. So I'm writing everything for scalars, but when I'm actually doing this, this is a vector of Brownian motions with a covariance matrix, which is identity. I've given you the scalar version of it.
Matrix, or is it
it's a matrix if I'm doing whatever. If I'm dealing with this as a vector, it's a matrix. But I'll write everything as a scalar. It becomes just easier. All these things are actually, the way it will be written in the book is all for matrices and vectors. But all the calculations I'm going to do, just in the interest of time, is do it for scalars.
In sigma B, is it only a diagonal?
No. So, yeah, in general, it can be sigma ij, some matrix of sigma ij's. So coming back here, if f, so let's look at also, if f is a smooth function, and let's look at the coordinates, it's a higher order term. Okay? So it will be f of t plus h minus f of t whole square. So I'll use a Taylor's expansion of f of t plus h, which is f of t plus h times the first derivative of f, h squared times the second derivative, h cubed times third derivative, and so on. So now I can cancel f of t because I'm centering around f of t, which gives you h f prime of t plus h squared term and so on. But I have a whole square outside, which means that even the first order term, h, will become an order h square, which is why even for a smooth function, I can ignore all these higher order terms. But what about a Brownian motion? Can I do exactly the same thing for that? Okay. So I have bt plus h minus b of t whole square. What do we know about the Brownian motion? It's zero mean, which means that the expected value of bt plus h minus bt is zero. But what about the expected value of the square term? Well, this is nothing, because zero mean, this is nothing but the variance, which means that this is equal to h and not h square, which means I cannot ignore second order terms when I have a stochastic differential. So that's really the difference in calculus when you deal with ODEs versus SDEs. In ODEs, I can do Taylor series first order approximation and move on, no issues. Here, I need to do Taylor series to second order all the time to be careful. If we just do that, everything falls out. And that's what I'm going to do today. Okay. So first, I'm going to consider a generically equations form. dxt is mu or b or whatever dt, this is a drift, plus sigma dbt. Okay. This is I've been saying that this is a Markov process. Roughly, the reason it's a Markov process is the following. If you look at any point in time t, the Brownian motion is independent increment. So anything that happens in the past does not affect how the Brownian motion is in the future. xt is already the current state. So to move forward, I need to understand how the Brownian motion, I need this noise, which is independent in the future, and the current state times dt, the time interval, which we know. So you can see intuitively that this is Markovian. And under nice enough conditions, so B is Lipschitz, sigma is Lipschitz, and so on, I can actually say that this SDE has a unique solution and things like that. Again, I'm not going to get into the technicalities. That's not the point here. You can read Oxendahl for existence of a solution, uniqueness, and things like that. It also has something called a strong Markov property. But since I'm not going to use that today, I'm just going to skip talking about it. But these notes, I'll have it available. You can look at it and look at the references offline. The most important thing for today is to try to understand how does the density function of this Markov process evolve. So again, the question is the following. I have a generic SDE of dxt is bdt plus sigma dbt. Okay? So I started with some initial random condition, which means at every point in time, xt is a random variable. Presumably, it's a nice random variable and has a PDF. Okay, so there are questions, of course, that PDF exists and so on. I'm not going to address any of that. I'll just assume that the PDF at every point in time. Okay. Then, can I actually figure out what this PDF is, and how does the PDF evolve? That's exactly what the Fokker-Planck equation is. Yeah. It could be both space and time dependent. In general, B could be B of xt comma t, sigma of xt comma t. I will bury that notation, but all this theory works for all those kinds of settings.
So if we have this equation, I take a super simple case where B, like this is bxt by dt is equal to bxt plus. I just put dt in the bottom. And now suppose I have bxt being 0, right? So I have 0 drift.
And I have pure diffusion.
Yeah, and sigma is a constant, right? Then I guess they call that a pure diffusion.
That's called Brownian motion.
Okay, so then if I have an x0, which is a random variable, after time t, I have a new random variable. And that will just be the original random variable plus a Gaussian with variance sigma t.
Correct. No, integral of sigma s.
Yeah, but sigma is constant. So
it's sigma times t.
Sigma times t. Right?
Yes. So that's right.
Yeah, okay. So this is the baby case of this thing.
Yes. So what you're, in particular, even sigma is 1, then what you have is the marginal being Gaussian with 0 mean and variance equal to t. That's it.
Yeah. So the intuition I had when I saw this in grad school, the last time I saw it, was that you're adding this little baby Gaussian, right? You're adding baby Gaussians at every time, except that, in the differential equation form, they become like.
There are two things that are happening. There's a drift. Something is pulling it in one direction, okay? And there's this adding a little bit of small, tiny little Gaussians, which is shaking it around.
So the mean of the variance of the baby Gaussian depends on it, right?
For example, if sigma equal to constant, it does not.
Right.
Okay. It could.
In general, it could. But as you think of it as if a discrete time, it would be I'm adding the baby Gaussians and everything.
That's right. That's right. You're adding, if you discretize it, but you're in discrete, you should be very careful how you discretize, because I pointed out that second order matters. But other than that, yes. Okay. So what I want to right now do is understand exactly what. So you actually told me what the PDF is for this special case.
Yeah.
Let's see how the PDF evolves more generally when I have a B and sigma. Okay. So if you once we understand it, a lot of things will just follow by playing with that equation. Okay. This equation is called the Fokker-Planck equation. It's also called the Kolmogorov-Forward equation. It's also called the master equation. There are many names for the same equation. Okay. I'll first flash the equation, okay, and then we will derive it and then come back and see what exactly these different terms are. Okay. If you haven't seen this before, then this is going to look mysterious. Okay. So it says, look at the PT of X here is the density at time t. Okay. This PDF, PT is the PDF at time t. So I want to look at the time derivative of the PDF. So how does the PDF change over a small interval of time? It says it depends on mu time, the spatial derivative of the field times P. That's one term. And the other is the second derivative of P. Now, this doesn't give you much intuition when I just write it this way. Let's derive it. Let's deconstruct it for several special cases, and then come back and look at this equation. So I want to look at first one special case, which is the other end of what Sujay said. I want to look at when there is no diffusion at all. So let's look at this equation when there's no diffusion. Txt is b dt. Okay. So there's a vector field B, okay, which is driving this particle. I start a particle somewhere. It's driven along by this vector field B to get to some point. So what's happening? Well, this, if you go back to your undergrad mechanics or whatever class you saw, is something called the continuity equation. Okay. It says that if you have density, then there's conservation of mass, and so you need to conserve flux. Okay. And the equation that comes out of this is del P by del T. How does the density evolve? Plus del dot mu P equal to 0, where mu is a vector field. This goes back to your essentially physics when you studied the first time you started studying physics in a vector field. Okay? That's basic. This is continuity or conservation of mass. So if you now go back to the Fokker-Planck equation, the first part is exactly that. You're saying del P by del T is negative of divergence of vector field times P. Okay, so that the deterministic part is behaving exactly like conservation of mass. Now let's look at the other side of it. Now let's assume that there is no drift at all. this is what Sujay was talking about. I have just a diffusion field. The nicest diffusion field we know about is this equation. Del P by del T is Laplacian of P. This is called the heat equation. If you have temperature, what happens to temperature? Well, you look at the average temperature, temperature diffuses. It diffuses based on the average temperature around your local point. And that's what the Laplacian is capturing. Okay. So del P by del T is Laplacian of P. If you expand the Laplacian, Laplacian is nothing but the trace of the Hessian. That's the operator. So it is nothing but summation del square by del x square of P. So now you go back to this. The Fokker-Planck, the second part of the Fokker-Planck says exactly that. There's a del square by del of P. And the thing is that because the diffusion coefficient could be different in different parts of space, you need to reweight this appropriately. That's what this Dij is. So the Fokker-Planck equation just puts together the continuity equation at one end and the heat equation at the other end. Okay, it says that there is conservation of mass. So it says the measure should evolve such that the conservation of the PDF should evolve such that conservation of mass holds. And because there is this diffusive element, you have heat-like behavior where there's sort of diffusive flow, and that's exactly the heat equation part of it. Okay? So this is the Fokker-Planck equation, just the sum of these two things. Now, let's actually derive it in one dimension because it's actually worthwhile to see exactly how this happens. By the way, this comment I made about continuity and heat is actually very important because, again, from classical physics, we know the duality between continuity and heat. Meaning, if I have a vector field in which things flow, whereas heat is diffusive, I can interpret a vector field as a heat flow and vice versa. This goes back 50 years at least. And this actually is the important reason why we can go between ODE and SDE. So it's what people call flow-based models for generation and stochastic differential equations or DDIM and DDPM in the language of diffusions. This connection essentially follows from this continuity and heat equation duality. And I'll point this out in about 45 minutes from now. Okay. But before that, I want to derive.
Probably a silly question, but you're assuming you have a density.
I'm assuming that density exists. I'm not going to talk about uniqueness, existence, or any such thing here.
Sujay's example where I start at 0, I don't have a density.
No, I will start appropriately. I'll start. So if I start a ODE with a random sample, then there's a density that continues to evolve.
Yeah, so you can start at a point.
It's a delta function.
The delta function.
Yes. Then the delta function. So in that special case, there's a delta function, and the delta function evolves as a delta function at a different point if there's no new randomness added to it. This is a special case where sigma equal to 0. Mathematically, it's uglier because I'm assuming it breaks, but essentially what I said is true. Okay. Just if I deal with delta functions in it, again, mathematically, you need to be much more careful than what I've done here.
Yeah, the reason why I'm worried is eventually you're going to reverse time. And you're going to go from a density to a...
Density. You will see that I will never go off a density.
So you won't start at 0.
I will not. I will start with a random sample. I will initialize from some distribution P naught, which is supported over 0 to infinity, minus infinity to infinity. Yes. And so I'm okay. Okay. Yeah. Let's actually derive the Fokker-Planck equation. Now for a 1D case. Everything I talked about holds for higher dimension, but let's do it in one dimension. So what is the one-dimensional version of Fokker-Planck? The rate of change of density is equal to the negative of the spatial derivative of vector field time density plus the diffusion term. So we want to show this. So the way we prove this is the following. So let's see be any continuous differentiable bounded function. I'll assume how many ever derivatives you want, you take this. Okay, I'm not going to deal with the technicalities here. So let us look at time derivative of expected value of C of x of t. Meaning I'm applying this function to the random variable x of t at time t. Well, what is this? This is roughly this derivative, I can take it inside the expectation and approximate this by saying that this is nothing but C of x of t plus h minus C of x of t divided by h, but h small. Okay, I'm just doing a small approximation. Now, let's expand this out. So x of t plus h, it's a diffusion. So I'll write it as x of t plus mu of x of t the drift times h plus sigma x of t delta bt. I'm just putting what I think of as an SD minus C of x of t. I just stick that in and see what happens. Let's expand this out. Now let's do Taylor's theorem. So Taylor's theorem, this is xt plus some delta 1 plus some delta 2. There are two different perturbations. So what do I get? I'll get c of x times c prime of x times the first perturbation plus c prime of x times the second perturbation plus c double prime times delta square, which is the first perturbation square. So I'm treating this as the first perturbation, this as the second perturbation around this point x. So I'm just doing Taylor series, but I'm making sure I'm keeping up to second order terms. Is this viewable? Okay. So let's do that here. So I'll get c of x of t times c prime of x of t times mu times h. Then c prime of x of t times sigma times this difference. Then there's c double prime of x of t times this one square. Then c double prime of x of t times this one square. And then c double prime of x of t times this one, because it cross terms. Let's look at, so I have all of those written out. That's what we've written here. So I have c of x of t, but I've centered it around c of x of t, that cancels. There's c prime of x of t times mu times h, we'll leave it alone. There's c prime times sigma times the difference in Brownian motion, but I have an expectation here. This is a zero mean, so I can get rid of that. This one, again, there's a difference in Brownian motion. It's zero mean, so I can get rid of this. There is then c prime, mu square, h square. This is a h square term, so I'll get rid of this. And then I have c prime, sigma square. There's a square of Brownian difference, but I know this expectation is h, so I'll replace this by h. So if I do all this, then I get something quite, so the only terms that survive are this one, c prime mu times h, and then c double prime sigma square by 2 times h. The h comes because of the Brownian motion square expected value. Now it will cancel with this h. And by taking limits, essentially we get the following evolution. Okay. I haven't done anything beyond Taylor series to second order. That's all I've done so far. I get del by del t of c of x of t, the expected value is c prime times mu plus c double prime sigma squared by 2. Now, this is a standard trick that's done in all these flow when you're doing continuity equation calculations. How do I rewrite this equation so that I don't need c prime or c double prime? I want to somehow convert this c prime to mu prime times c. I want to convert the c double prime times sigma square as c times something else. Okay, this swapping of higher derivative of function to its coefficient is a standard trick, and we are going to do this. This is essentially by integration of parts. And so let's actually write this out and see what is going on. First, why do I want to write this as c? If I could write this as c times something plus c times something else, then I can say that there is c del by del c of something is something, there's a c all the way there, and the multiplier of c is the same somewhere, so I should be able to extract a PDE out of this. Okay. I'll do this a little bit more formally in just a second. Let's expand. So what I have is an expectation of x of t. So which means it's integral. This expectation means it's just an integral with respect to the density of x of t, which is all I've written here, times del by del t. This expectation again, there's a density. That's what this expectation becomes, the integral. So let's first look at this. I can take this derivative inside and write it as c times the derivative of the density. Yes.
No, can you write beside the screen?
Yeah. Is it any better? Is it better?
Not long. You can get it. Yeah.
I'm doing some multi-dimensional optimization. Is this any better?
It's fine for me, but
Okay. All right. Okay. So I have the derivative of this. So I can pull the derivative inside, saying c times the derivative of the density. That's one part. Now let's look at the second term, which is this. C prime times mu times p. That's what I have. So C prime times mu times P. The basic integration by parts trick I have is the following. UV integral of U V prime plus integral of U prime V equal to U times V. This is integration by parts. So I'm going to call this as U prime, this as V. Then what do I get? Integral of U prime times V equal to U times V minus integral of U times V prime. This is V prime. Okay. So we have just written the parts. So this basically moves a U prime to a V prime. Okay, that's essentially this. Of course, it leaves this pesky UV. And so you need to use boundary conditions to kill that. So we know that this is a nice density function, meaning at plus and minus infinity, the density should be 0. So that means since I'm integrating between plus infinity and minus infinity, this term goes. So which basically gives me that that basically C prime times mu, this integral can be written as C times negative, there's a negative sign, of derivative of the vector field times P. So you see where the continuity equations mu times the density times the vector field comes from. It essentially comes from this integration by parts trick. Okay. Now, I have C prime. Now I have the second term. Because C double prime times the variance, sigma square times P. I need to do integration by parts twice. Because each time I had to get rid of the C, I have to bring C double prime to C prime and then down to C. I'll do this 2 times. So the first time I do it, this is V, I'll call this as V prime and this as U. Then I'll get V prime times U is V times U prime. Okay. There's a UV term, and since I'm going to integrate from negative infinity to infinity, there's a density, this part is 0. Okay. So I've gotten this down. I've gotten C double prime down to a negative of a C prime times some derivative. So now let's look at this integral, C prime times this. I'll call C prime as V prime, and I'll call this as U, and do integration by parts again. Okay. So then I'm going to get this one C prime will become C, but this derivative becomes a second derivative. And what I'm going to get here is derivative, I get something else between minus infinity and infinity. So this has a del by del Z of PT. So if you make the assumption that this quantity is 0 at both plus and minus infinity, which essentially means not only is the density going to 0, the derivative of the density is also 0 at infinity and minus infinity. Okay, so it's going down fast enough. Okay, so that's what essentially this means, as long as sigma is bounded and so on. Then this is stronger than sort of properness of random variables. But if you make this assumption, then you're essentially there. You've got second derivative of C prime times something is C times second derivative. Now you again see where the heat equation second thing is coming from. It's coming from this part, which will give you this delta, this second derivative. So if you put everything together, what do we have? C times the time derivative of P is equal to C times the spatial derivative of the vector field plus C times the second partial of the variance term. And this is true for any function C. And therefore, we can conclude that this inside thing must be equal to the sum of these 2 things. And that's essentially the Fokker-Planck. Yeah. Let's go back there. I'm just assuming this integral is well defined. So
if you get, it may not hold it in.
You have all, I mean, you are doing all these exchange of integrals and derivatives. If things are bounded and nice, then these all, some of these convergence theorems are useful, and you can. By the way, this is not the way you formally prove any of this. Okay, the formal proof of Fokker-Planck is very different. Doesn't require these kinds of assumptions. So let me get to that. I'm telling you why this thing comes. This is an intuitive argument. Really, what you need is something called Dinkin's formula. Okay. You go through Ito calculus, and Dinkin's formula is the equivalent of fundamental theorem of calculus for stochastic losses. Okay. It basically tells you that what's the fundamental theorem of calculus? F of B equal to F of A plus integral A to B F prime dx. So this says that expected value of F of X tau at some stopping time equal to F of X plus the expected value of some integral from 0 to tau of A, which is a generator of the Markov process. So you go through that, you'll get this, and then go through something called the adjoint equation for that. You're going to get Dinkin's, you'll get Fokker-Planck. But with the extra assumptions, I think this is more transparent for us to just see what is going on, where all these terms are coming.
The exact set of assumptions that should prove that.
Okay, so this is the vector. B is a vector. B and sigma are jointly Lipschitz. It's an Oxen. You can look at chapter 4 of Oxendahl, which will tell you exactly the same. I can't read. I can read it off, but it's right there. Okay. And yeah, right now I can't tell you. Yeah, once you get that stuff, you can get these things. Okay, so right now what we have so far is the Fokker-Planck equation, which says how does the density of any SDE evolve? How can we use this? Then let's look at a classic SDE called the OU process or the Austin-Uhlenbeck process. It is the following. dxt is minus xt dt plus root 2 dt. So the diffusion coefficient is constant. The drift is just pulling it towards origin. So let's, in the d equal to 1 case, what's the Fokker-Planck equation? Well, del by del t of pt is negative of the vector field. So minus of minus x is just x times the density plus half times root 2 square, which is just 1, times del square by del x square of pt. So this is the density evolution of the Fokker-Planck equation of the OU process. And let me try to work this out in steady state, meaning I'll set t equal to infinity. If I set t equal to infinity, the time derivative is 0 because quote unquote this is steady state. So I just need to
The relationship with the time.
So Stein's lemma from my, I don't know which Stein's method Adam is talking about, but the Stein's lemma, which I have in mind, tells essentially it's a version of the thing. It basically says expected value of the generator of f of x equal to 0 or expected value of f prime of x equal to expected value of x f of x for a Gaussian. Okay, this is essentially a characterization of not the time varying density, but at stationarity. The Stein's lemma tells you what happens to the equation. Okay, whereas what Fokker-Planck is telling you is actually how the density evolves over time itself. So one answer to Adam's question could be this is a transient. The limiting of this will get you that what Adam is asking about, but this is a transient evolution. I'm not sure if this is what Adam was looking for, but I can chat with him offline. So I'm right. So Fokker-Planck. Yeah. All right. So now I have this Fokker-Planck equation for density evolution. Let's look at the steady state. Okay. In steady state, you are going to get, if Adam, if you look at this equation, this is essentially Stein's equation. Okay. So I'm going to set the derivative of time derivative of the density equal to 0 and set t equal to infinity. So I'll get x times derivative of p plus p, just expanding this out. X times p, if I take the derivative, it's 1 times derivative of p plus x times 1 times p plus x times derivative of p. That's the chain rule plus second derivative of p. So I'm just going to guess that the solution of this is e to the minus x squared by 2 divided by root 12. You stick it in and check. It actually works. Okay. This is actually the right density. Good. Because I know I'm just positing that this SDE has a unique solution. This is some other theorem. Okay. Which is why I said right up front. I'm going to assume that under these conditions, somebody has proved there exists a solution, the solution is unique, and I'll just continue. So now, any of the proofs I'm going to do is not going to try to show unique. I'll just pull out a solution and see if that fits in, and then I say this because somebody else has done that work of uniqueness.
Just an question. Does there exist SDEs that are?
Yes. So again, you want to ask whether there's a strong solution, does it have weak solution, and all that stuff. So I don't want to go down this SDE thing. These are all what you're asking are valid questions. But again, we can chat offline, but right now for this, I want to just stick to the nice, clean setting. Okay. I'm happy to chat with you offline and point you where all the conditions for these kinds of solutions. Yeah. So this is what I claim is a solution. So if I take a derivative of this, I get an x times e to the minus x squared by 2. And let me not go through the calculations. You can read this if you want. I've told you what the differentially this equation I need to satisfy is. I stick in P is e to the minus x squared and see that that equation is satisfied. Let's start. And therefore, what is the takeaway at this point? If I start this stochastic process with initial condition from P0, then the steady state is Gaussian. In fact, we have shown something further. Start from any initial condition. It doesn't matter whether it's P0 or not. Eventually, you're going to get to a Gaussian in this Markov process, because that's the steady state of this, assuming that this thing actually comes. But we are not going to use that. We just say, start from the distribution of images, run this, you'll get noise. Now, what we want to do is to reverse this process. We will call this process we talked about as forward process because it starts at t equal to 0 with x0 being p0, the distribution of images. And as time evolves, pt of x goes to a Gaussian. That's what we have. So for this part, because I'm going to talk about forward and reverse, I'm going to change the notation. X is going to have an arrow on top to say it's forward. So this is exactly what we discussed with the forward distribution. And the distribution of x forward at time t is p forward at time t, which is exactly what we derive using the Fokker-Planck equation. Now let's consider. So this is going to run from 0 to infinity. Again, because we are going to be for technical, I don't want to deal with technicalities. We are going to stop at a large time t, okay, and reverse the process starting from that point in time. What do I mean by that? We want to construct a stochastic process where time runs backwards. How do you implement it? We'll worry about that in a second. But right now, time is going backwards. I mean, time is starting at capital T and going down to 0. This differential equation has initial condition. I'm putting an arrow backward on top of it. So this is the x capital T is sampled according to the forward processes PT, which is almost a Gaussian. Okay, I'm not sampling from a Gaussian so that I can make the coupling clean. I'm just sampling from P forward at capital T. That's my initial condition for my new one. And that is x backwards at time t is identically distributed to x forward at time t. And we want to construct this SDE's evolution such that we further have this extra property. Even at time 0, x forward and x backward are the same. If we do this, then you see this SDE running backward would give me at time 0 a sample from images. So this would be a generative model because I can start from this distribution, which is almost a Gaussian. So I'll just actually initialize the Gaussian, run this SDE, and then at time 0 backward in time, I'll actually get an image. This is what we mean by running the reverse process. Sujay.
You want to reverse SDE?
No, not yet. I want to construct. Now I'm going to do it in 2 passes. The first time, I'm going to just give you an SDE and just show it the right way. Yeah. The second pass, I have time for both, is to show you why that is the right SDE. And I want to derive it using the heat continuity equivalence.
Yeah. So I just make one more comment. So the dumb way to understand OU that I had, when I was a child, right, is that you have the current x at time t, and then if you want to go to the next step, you just scale down the x by some 1 minus h, and then you add a small Gaussian with variance h. Right, and then that is the OU process.
That's a discrete OU process. Okay. I think of it as just an attractive field. Minus x means further away, you're pulling stronger towards origin. Okay, you've got a field which is pulling towards origin. Far away, you're pulling faster. Small, closer, you're pulling slower and slower. Okay, but you're adding a little bit of noise on top of it.
You're pulling multiplicative. You're not pulling.
You're not pulling additively. You're pulling multiplicative
with a constant multiplication term.
Correct.
And the original whatever x you have is getting forgotten multiplicatively.
Yeah, exactly.
And the Gaussian is filling it in.
Yeah, that's right. That's all this is.
And then now you're going to reverse this.
Now I'm going to reverse this. My claim is the following. Okay, let's call this new reverse process x back of t.
Yeah.
And it's going from capital T to 0. We are going to define a new SDE, which is the following. Its diffusion term is still root 2 d pt, exactly the same. I'm putting b tilde because there's another copy. It's an independent copy of a Brownian motion. But the drift term is not just minus x, which is OU, but has an additional term, which is grad log pt forward of xt backward. Okay? Meaning, look at the forward process's density at time t. Suppose that there's a black box that gave me gradient log of forward process density at time t. feed the black box with the current state of the reverse process, and get a drift term out of it, which will add to the multiplicative thing, which is -6. And this is my reverse process. I'm good. Why is this the right thing to do? It will be obvious after in another 15 minutes why this is the right thing to do. But right now, I'll just, it looks a little mysterious, this grad log P, but let's just work with it and we'll come back in. I'm running time backwards, which is another weird thing. I'm going to turn the time around in a minute. Time flows backwards. I started. So this equation starts at capital T initial condition, and then every tiny step forward is T minus delta T. Okay. What that means is slightly unclear, but I'll do it. I'll show you what it means in a second. I'm just formally stating that this thing runs backwards in time.
Yeah, or maybe the way to answer that question is like the forward equation is playing the videotape forward in time. Now you're playing it rewind, and that transposes to a new equation, and this is what the new equation is.
I don't. Let me turn the reverse process on. Okay, I completely agree with your answer. But I think I'll give a different answer.
The trajectories to look the same.
No, it's a sample path to reverse. Okay, yeah.
Okay. Yeah, sample path, but and if, like the both statistics look the same.
Yeah.
But your differential equation will as a result be different. If nothing else, because it should depend on P0. Like so the forward thing didn't depend on
exactly.
Equation didn't depend on P0.
Here you're driving towards P0. Exactly, because you're driving to P0, so it has this PT in it.
But it's T minus H minus X.
Yes, exactly. Exactly. Okay, that's what you're asking. Yeah. So my delta is of x to t plus h minus xt. It's x of t minus h minus xt. Okay. So the claim is for all t between 0 and t. In fact, it's a stronger thing. The forward density and the reverse density are identical. But this is not sample pathwise true. It's only for every marginal it's true. It's not a trajectory statement. For every time t, the forward density and the backward density are true. In fact, now let me tell you, this
forward density is the solution to that.
The backward density is this equation's formal PDF at any point in time, which I have to derive now. Okay, and we have to show that these are equal. In fact, something interesting. So this is attributed to Anderson 1982. This is in the literature, and this has been used by Song, Hermon and Song, and several others. This particular result of reversal. Historically, Anderson showed something stronger than this. Not just that, he was interested in trajectory reversal. Okay, so this is a special case of his result. This particular result. So Srikanth and Bruce, I had a discussion when I was talking about this in Allerton, and Stratonovich seems to have had a version of this in 1950s. So the point is, this thing goes back almost to antiquity, these equations. They're known for a long, long time. So a scalar version of this was in some article in 1959. So for those of you interested in the history of it, well, there's a long history of this stuff. But let's actually consider the reverse SD. Okay, this is what I wrote was the reverse SD. First, this time reversal is a little weird, Constantine. So what we are going to do is to flip time around. So we'll change T to capital T minus little t. So I will formally just reverse time. So it's a reverse process running forward in time. Okay, that's what we are doing. I'm still considering the reverse process, so meaning the x is back. I'm just trying to doing the time direction. I'm just making the flow of time move forward. So t becomes capital T minus t. That's what we are doing at every one of these things. I'm just changing t to t minus t. In every one of these, dt becomes dt minus t. The Brownian motion, dt minus t. Okay. Now, d of t minus t is minus dt. Brownian motion, I don't care. If the Brownian motion flipped around is another Brownian motion. So I'll just call it some other Brownian motion because I only care about distributionally equivalent solutions. I'll just call it b hat of t, some other Brownian motion. Okay. So what I have is dxt minus t, exactly the equation I wrote with t minus t. Some signs have changed because of the this thing. Now I'll call yt as the reverse t minus t. So this is the equation we finally get. This is the reverse equation running forward in time. Okay. YT. So I'm basically playing this. So Sujay's analogy, I'm running the tape backwards, but I flip the time around and running the backwards tape forward in time.
I have a question. So another way to interpret this is maybe the following. I start with a P0. The OU process gives me a PT. That is the X process.
Yes.
Now forget about the reverse, whatever, I don't care. Right? But now I want to make a new process so that when I start with PT, I end up with P0. And that is why. And this is the equation for why. Right. So that's the takeaway.
That's it.
Like I don't need to think about all this reverse,
I'm going through all this to show the equivalence. The reason I'm doing all this is I know how to run the Fokker-Planck equation for things running forward in time. Okay. So for this, I'm going to do the Fokker-Planck and see what happens.
Yeah.
So
but you could have made a theorem, which is, here you just pull this out of your hand.
That's right.
Now I will prove
Fair
that
enough.
if you start with P2, you get P0, end of the affair. You don't need to worry about all this.
I do for one reason, because otherwise I need to look at time T versus capital T minus little t. The equivalence is not the same times for the X and the Y process. Because the density of the X process, because of the time change, I need to look at what is happening at time little t in one equation is what's happening in the other equation at time capital T minus little t. I don't want to deal with that, which is why I did all this stuff. So I can align time, that's all. But but what you're saying is also true. So let's write YT as the density of PT. Okay, the density of let QT be the density of YT. So the Fokker-Planck equation for YT is the density of. So I look at this. So this is my drift field. This is my diffusion. Stick it in the Fokker-Planck, and so I'm going to get vector field times density, second derivative of density. Exactly the same thing. Okay. The important thing to notice is the forward operation. Now let P backward be the PDF of the backward equation. What do you get then? Then P backward is Q of T minus T, because that's all I've defined because of the time reverse. So I'll stick that in. So the density of the P backward has a P forward times a P backward. So this is because of the drift field, this part, and this is because the Fokker-Planck has a density term. I just stuck this. I've just formally stuck in whatever you've gotten so far. So let's look at this equation. So let's flip time once more. Okay, I'm going to call T minus T back to S. And if you work through if you trust me on just keeping the calculations correct, what you finally get is the density of the time derivative of backward density is the spatial of X times P back plus spatial of, there's a log of P. In scalar, the derivative of log P is basically 1 by P times the derivative of P. Because derivative of log of function equal to 1 by function times function derivative itself. So just chain rule. So we have done that. So what do I get because of that? I get, this is a forward. So I get a 1 by P forward times P forward. There's a P backward. Diffusion of P backward. Now I claim that P forward is same as P backward. I'm assuming every solution is unique. Okay. So if this is indeed true, let me stick in P backward is same as P forward is same as P backward is same as P forward in this equation, see what I get. If I just change this to forward, that's my guess of the solution, and see whether this is true. Okay. And the answer is yes, because this and this cancels. This second derivative, well, this is derivative, there's a second derivative, there's two that cancels with one of these, and we will exactly get the Fokker-Planck for the forward. And that's the proof. Okay. So what we have shown is this is indeed the reversal in the following sense, that at every time in the marginal, this matches what you want. Okay, so what we have done so far.
Marginal means at a particular time.
At every time. This is whenever I mean marginals in this, I mean time, marginal at time, not in terms of coordinate or any such. Because you could ask, how is the joint distribution over multiple instances? I'm not talking about any of those kinds of things. This is all just marginal calculations. But since I only want a sample at time 0, marginals are good enough for what we are doing. So this is what people call, this is essentially the math behind DDIM and they do. Not DDIM, DDPM. Okay. Denoising diffusion probability model. We'll come to I in a minute. We are just talking about, we are still talking about just SDE models.
And your initial conditions are PT, not the Gaussian.
Yes, formally. In practice, you just start from a Gaussian because PT is close to a Gaussian anyway. Okay. But formally, for this to work, your initial condition is PT, which is exponentially close. Yeah. It depends on how that Markov chain mixes and how close it gets to a Gaussian and all that kind of stuff. But if you run large enough, then you're good. So this assumed the forward process, you could diffuse forward, you could move it forward without any knowledge of any densities you wanted. Whereas the reverse has a grad log PT in it of the forward, but we don't know the grad log PT of the forward. Okay, so how do we figure this out? So this is called Tweedie's formula, denoising score matching. Okay, there are several approaches. This approach goes by, it was proposed essentially by Vincent in 2010, but this goes back to work by Tweedie in 1950, and in Efron's papers in 2011, this was discussed, and this is today as far as I understand, the type of score matching that's used. So what is the idea? No, it was about the score matching. Okay. Score matching is of interest, I think, for various other reasons as well. So, but here I just want to talk about how to use that box for estimating grad log PT. And the answer is actually this. The idea is actually the following. Okay, suppose I have access to a large collection of samples of images. So this is what I'm going to denote as P0, sample X0 from P0. So I have just lots and lots of such samples. We can noise it, meaning let me define a random variable X sigma as X0 plus sigma times Z, where Z is just a Gaussian. Okay. This is basically, I'm just convolving. So I'm adding noise, which means I'm convolving the period. I'm convolving P0 with a Gaussian of variance sigma squared. Yeah. That's the same thing as adding.
OU has a multiplicative.
This has nothing to do with OU. No, I'm talking about something independent of OU. I am talking about a separate calculation of just two random variables. Yeah. I've switched out of diffusions. I'm just talking about how you do this. Maybe you do OU, you do something else, maybe you scale, whatever. Yeah. I'm just saying, suppose you had access to a bunch of images and I could noise it in this way. Okay. Then, and I want to use mean square, MMSE, to denoise it. Okay. Why? Because I just felt like it. So, meaning I'm asking you the question, if I'm giving you a sample of X sigma, can you figure out what is your best estimate of X0 in terms of mean square error? And the answer to this from your undergraduate probability class is minimum mean square estimation, which means you take the conditional expectation of X given X sigma. This is your MMSE estimate. Now, neural networks are very good for doing these kinds of things. If I want to find this condition, if it's a linear thing, you know how to do this MMSE in closed form. But in general, we don't. But maybe I can train a neural network to learn this function well. So meaning let theta be the parameter of a neural network, then I can figure this out by least square, meaning the following. I will minimize out this class of functions g theta, x0 minus x sigma. So this is my original image. This is a noisy image. Solve this mean square estimation problem. Okay, and I can learn this function then. So now I have a box that can learn this. I still haven't got to the score function, but I have a box that can learn this conditional expectation then. Now there's an interesting property, which is Tweedie's formula. Suppose I have X0 from any distribution P0. Z is a Gaussian. I'm writing it in a scalar case. The same thing holds for vectors. And X sigma is a distribution which is from this convolution. Then the conditional expectation has a closed form formula, which is X plus sigma square times grad log P sigma X, where P sigma is the distribution of X sigma. This is Tweedie's formula. Now, I want to know the score function. I have a method to figure this out. And therefore, I can just subtract X0 and divide by sigma square to learn the score. How you implement it, there are a bunch of different ways to implement it. But essentially, this says what is the relation between score and conditional expectation. Why is this true? The reason this is true is the following. Let me do the special case of y is x plus z. This is all scalar. X is any distribution P. Z is a Gaussian. Y has the distribution Q, which is P convolved with the Gaussian. Then what's the conditional expectation of X given one? Well, that means it's nothing but X times the conditional density dx. Okay. Which means it's X joint density divided by the marginal times X. So which means it is x times y given x times f of x by f of y. I'm just doing Bayes' rule in multiple steps. So I have f of y given x, f of x. This I can pull out the integral because this is dx. Let me now stick in what I have. F of y is q. So I'm going to put in q. F of x is p. What's y given x? Well, if I gave you x, it's just a Gaussian with shifted mean of x. So y given x is just a Gaussian with mean x and variance y. Y given x is that. Substitute that. So what is E of x given y? It is nothing but 1 by q of y. I'm just substituting here x times, this is the Gaussian, I put it in there, times of x, p of x. Okay. This is the expression for conditional expectation. Now, q of y, that's the distribution of y, is p of x's distribution noised. So convolve with its Gaussian. So let's do the convolution. That is p of, so x is my dummy variable in this integration, p of x times this one, y minus x squared dx from minus n. I've just done the convolution. So now, therefore, let me take the derivative of this with respect to y. Okay. Del by del y of q of y. So I can take so these limits are minus infinity, infinity. So I can take the derivative all the way inside. So the y only appears here. So it e to the minus y minus x whole square by 2 times the derivative of this, which is 2 times y minus x by 2. If I do this and just stick things in, then derivative of q is, there's a y here, so negative y times p times this plus x, the other side, x times p times that. Now look at this. This is p, which is f of x. This is f of y given x. So this product is the joint of x and y, which means this integral is the marginal of y, because I'm marginalizing it out. The joint of x and y. This one, we just saw xp times this is conditional expectation. Xp times this is conditional expectation divided by q. So if I take q to this side, then what I have is derivative of q is minus y times q of y plus q of y times the conditional expectation. Okay. So I'll divide both sides by q. So conditional expectation is y plus 1 over q times the derivative of q. But this is nothing but log q. This Tweedie square. That's it. Okay, the vector version of it. I just derived this in scalar from first principles. So the reason why this is interesting for this application is this quantity is what we want, but this is what we know how to learn from data. And so now you can actually get things to work. Yes.
So this, like operationally corresponds to adding Gaussian noise, right? And so now if I added a different noise to the image, right? Like some different noise, you can work out these things.
You may not get such a closed form formula. So the reason you're doing this is not because you want to add noise and denoise, but because you want to learn this. So the goal is not to learn the conditional expectation. The goal is to get this core function because I need this to run the drift of my diffusion, reverse diffusion.
Right, but this core function is, I guess, not a fundamental thing. It's not a noise distribution independent. It's like we care about this particular because we are doing Gaussian.
Exactly. If you're doing something else, you need to go back to the basics and just work everything out from. But now you see the pipeline for doing things. Absolutely. Right. Now, I have about 20 minutes left. I want to do the last part is flow models. Okay. So the high level idea so far is we construct an SDE running backwards in time to sample over distribution of images. Now, what we are going to do is to construct an ODE with a random initial condition such that the marginal distribution of that ODE at every point in time is exactly that of the SDE. Okay, so I'm not sure if that made sense. So let me repeat. So what is SDE? I start with any initial condition, I evolve it, I get a distribution, and that PDF evolves with time. That's what we did through the Fokker-Planck. Now, what I want to do is the following. You take any ODE, there's nothing random in it. I start with some initial condition, it runs through and it goes somewhere. But what if I run it with that random initial condition? Well, it will be deterministic condition on that random. But if I look at the unconditional distribution at any point in time, it's It depends on what my initial conditions distribution was and how that was pushed forward through the ODE's evolution. Okay? So I can formally write the PDF of if an ODE is initialized with a random initial condition, I can formally write what the PDF of that is going to be at any point in time. Okay? Assuming there's a solutions exist unique and all these kinds of things. And so now we want to construct an ODE which will have exactly the same distribution as the reverse system. Okay? And we'll see what it is. So we want to construct a time varying vector field such that I sample. So we'll do both the forward and the reverse. Okay? Now let's start from the forward. So I want to start from P0 and get to Gaussian in this ODE. So I'll start Z0 as a sample from P0. Then I look at the forward DZT. There's a vector field, forward vector field. It depends on, it could be time varying. It's just DT. There's no DWT or any such thing. Question. So if the initial condition is fixed, this is deterministic. Okay. But because I don't know what the initial condition is, at every point in time, there is a marginal distribution. And that's what I'm looking at. There's no, this has nothing to do with Fokker-Planck. I'm just constructing now a new sampler, an ODE-based sampler. Okay. We had an SDE-based sampler, which is the reverse forward process, the reverse process. This is an ODE-based sampler. I start with a random initial condition, which is an image, and run this deterministic evolution. Okay. And at any point in time, I will get a sample. Okay. And I want this to be a sample of a Gaussian in distribution. So meaning I start with many random initial conditions. The ensemble will have a Gaussian distribution and keep putting. Okay. So what is this vector field? And once we do that, I want to reverse this vector field, and I'll come to that in just a second. I'll come back to the reverse. But first, I want to go to I want to show you how you can take an SDE and make an ODE and vice versa. This is, I think, the key for all these things. So consider the SDE, dxt is mu dt plus sigma dpt. Okay. I'm doing everything for scalars, same thing's full for vectors. So what's the Fokker-Planck equation for that? The density is vector field times p plus second derivative of sigma squared times p. That's the Fokker-Planck for that SDE. Now let's look at the sigma squared times p term. Okay, there's a half sigma squared times p. There's a second derivative. I can write the second derivative as derivative of derivative. Now look at this derivative of sigma squared p. This can be written as chain rule. It's derivative of sigma squared times p plus sigma squared times derivative of p. Okay, and so I'll leave the sigma squared time derivative of sigma squared times p. Sigma derivative of p is nothing but derivative of log p times p. Because the derivative of log p is p prime by p, but p will cancel with this p. So I can write p prime as derivative of log p times p. I can always do this. And this is essentially what people call the heat continuity. So I've taken a second derivative and pushed it this way in a different form. I haven't done anything fancy yet. Now, look at this equation. This second derivative can be written as a first derivative of something times p. This is my box. It's del by, it's a first derivative of this plus this. There's a p common. So I can pull this into my drift term. My drift term was the form mu times p. Now, my diffusion term also looks like derivative of something times p. Okay, so formally I can just absorb it and write the derivative of the diffusion is that drift field we had minus this thing, this. So let's say that the variance is not time varying for simplicity. Okay, sigma square is 0. This goes away. That means you just get del by del x of log, which means a score. Okay, so this is where the score is coming. This is the equivalence between heat and continuity. If I've got diffusive heat, I can make it into a vector field by just taking the grad log p. Okay, I can move between. So anytime you see grad log p, you can make it Brownian motion. Okay, you can simulate diffusion in two different ways, either as dpt or by deterministic vector field, which is grad log p. This is known historically, and that's exactly the trick. That this is basically this particular trick. Once you see that, this is my new vector field. So for the OU process, what do you get then? The forward process, if I just do this, has x plus grad log pt of x. So this is very different from the OU process we studied earlier. The OU process, the drift term was just minus x. It didn't have any p plus pbt. Whereas now, the ODE's forward process has a grad log p in it. Okay. So it looks like it's complicating things because even the forward process requires grad log p, not just the reverse process. But ODEs are really nice because you want to reverse a field. What do? You just change the vector. Whenever you have vector field, change the sign of the vector field and change t to t minus t. Okay, and I get the reverse flow immediately for that. So there's no work that is needed once you have the forward vector field to go to the reverse vector field. In particular,
so let me understand this. STE and ODE. So there was a P0. Now I had some STE. It looked really simple. The equation looked really simple. The update rule, right? And it gave me a PT at the end.
P infinity, which is Gaussian.
Yeah, or a P uppercase T at the end.
Yeah.
Okay. Now what this is doing is saying, okay, I want this P0 at the beginning. I want this PT at the end. What is the ODE that will give me?
In fact, at every point in time as well.
At every point in time, like what is the ODE that will magically give me?
Exactly same in terms of distribution. And this is it. And this is it.
Okay.
And the reason this comes is because del square by del x square of p equal to del of grad log p times p. It follows from this equivalence.
Yeah.
Yes. P0. I'm starting both of. I'm starting the SDE from the distribution of images. I want to get to Gaussian at the end. So this is the forward process I'm doing right now. Okay. We'll come to the reverse process next. I've just done the forward process. Now what we have is a flow forward process. So what people call DDIM, that is this paper. Okay, Song et al. This is the reverse process corresponding to this. But once you have a vector field and a deterministic ODE, so I give you a deterministic ODE, x dot equal to v of something dt. How will you get the reverse of it? Any vector, if it's pointing this way, change the sign of the vector field. So, and if it's time dependent, change the time t to capital, and you're going to run it till capital T, change t to capital T minus t. And just through these two operations, you have reversed field, right?
When you're trying to reverse the ODE, is it somehow reversibility of a Markov chain?
This is, we don't need to go in. There is no reversibility of Markov chain here. We have an ODE, this thing. I just want to run the ODE. I want to reverse the ODE flow. There's nothing random here. There's nothing stochastic. I'm using the ODE. I'm feeding a black box deterministic transformation with a random initial condition. And it's marginally matching everything. Now, if you want to reverse this ODE, I just change the field direction. There's no transition kernel or any such thing for this.
Then what about the reversibility of
there? That Markov. So that Markov process is reversible, but that's a different story altogether. We didn't really use reversibility. Okay. Yeah. Because it's a stochastic. Yeah. Yeah. So claim is that if I reverse this, meaning I just change the direction of the field, then I'm done. Okay. And the proof is essentially just obvious. You just change the, you look at time, this is deterministic calculation. At every point, check trajectory to trajectory. If I'm here going this way, there I'm going that way. And that's all there is. Okay. So like so this, okay, 1 hour, 15 minutes. So you've seen sort of what I've done right now is covered sort of the mechanics of how diffusion generative models work. As I said at the beginning, none of this is original work. This using these diffusion models actually goes back to Saul Dickinson et al. The 2015 paper. Song and Armon in a series of papers sort of came up with generative models which work better and better. And right now, the state of the art. There's and combining sort of using this integrated SDE view was a 2020 paper, I think, score-based generative model with stochastic differential equations. So yeah, you can start from here, and there is maybe next other weeks you'll start seeing how you can use diffusion models in the future for various applications. I think that's what this seminar series is about. I'll stop at this point. Yes, Sujay.
So the first part, okay, so this is algorithmic view of diffusion, where you take a noise, you take an image, you keep adding noise, denoise it, right? And that seems directly related to the STE model. Now you converted that to an ODE. What is
why do you care? Because people are actually the current model with the DDIM, ODEs are much faster to run sample than SDEs. Yeah. So what we have shown is that there is an ODE equivalent which will give exactly the same distribution as the SDE. And ODE solvers are much faster than SDE solvers.
Okay, so an ODE-based algorithm would be take that image, just run the ODE, don't add any noise.
No, take the noise, take the reverse of the vector field we derived, the ODE-based algorithm. Yeah. Start from noise and run that for some time and stop.
Oh, so it's only run the.
Yeah, I don't need to use it in the forward direction at all.
Because the forward direction is easy anyway.
But why is the forward direction even useful? I used it only for construction. Huh? But that is something else. That's score matching something else. That's noising. The ODE reverse is the only thing that's useful for generation. Yeah. Okay. Gustav?
I'm not sure I